You know, in math and physics, some things just can't be pinned down with a single number. I mean, think about the wind or the path of a rocket. To really get what's going on, you need to know more than just how much. You have to know which way. And that's exactly where the tool we're talking about today comes in, vectors.
So let's start with a puzzle. Picture this. Your ship is trying to go straight east, but the ocean itself is pulling you south. Where do you point the ship? You can't just add or subtract the speeds, right? The directions are totally different. This is a classic vector problem, and it shows you perfectly why we need a way to work with both strength and direction at the same time.
To really get what a vector is, it helps to see what it isn't. And what it isn't is a scalar. On the left, you see speed 30 miles per hour. That's a scalar. It's just a number, a magnitude. It tells you how much. But look to the right. A vector gives you the whole story. Velocity 30 miles per hour northeast. That's a vector. It's got the how much and the all-important which way.
Okay, so we've got the big idea, but how do we actually, do math with these things? Well, the secret is to break a vector down into its basic building blocks. We call them components.
This right here is the heart of it all, the component form. The easiest way to think about it is like a simple set of instructions on a map. The A value tells you how many steps to take left or right along the x-axis, and the B value tells you how many steps to take up or down along the y-axis. Put them together and they point you to one exact spot. Now, take a good look at that formula. Does it ring any bells? It totally should. It's just the Pythagorean theorem wearing a different hat. The horizontal part A and the vertical part B are just the two legs of a right triangle. The vector itself, well, that's just the hypotenuse. Its length is what we call the magnitude. And hey, anytime you've got the sides of a right triangle, you know you can find the angles. That's where some basic trig comes in. The direction angle tells us exactly which way the vector is pointing. We just use the inverse tangent of the vertical over the horizontal, rise over run. But see that warning? Quadrant matters. Hang on to that thought. It's a super common trap and we're definitely going to come back to it.
All right, enough theory. Let's get our hands dirty and see how this actually works. We're going to take these formulas for a spin with a real example. So here we have a vector, v, and its components are 3, 4. To get its magnitude, its length, we just plug those numbers into our formula. So 3 squared is 9, 4 squared is 16, add them together, you get 25, and the square root of 25 is 5. Boom, done. This vector has a length of 5.
Okay, that's great. But what if we only care about the direction? What if we want to talk about which way something is pointing, without getting bogged down by how much? We need some way to standardize the length, to make it simple.
And that is where the unit vector comes in. It's a special vector whose magnitude is always exactly 1. Think of it like a pure distilled direction. And the formula couldn't be simpler. You just take your original vector and divide it by its own length. This basically shrinks it, or stretches it, down to a standard length of 1. Let's try it out with this vector, -5, 12. First things first, we need its magnitude. So -5 squared is 25. 12 squared is 144. Add them up, you get 169, and the square root of that is 13. So our original vector has a length of 13.
Now for the cool part. To get the unit vector, we just divide each of those components by the magnitude 13. Our new unit vector is -5/13, 12/13. And here's the key. It still points in the exact same direction as the original. But now, its magnitude is a nice, clean 1. We've successfully isolated its direction.
Okay, remember that warning I told you to hang on to about the direction angle? Well, we're back. And listen up, because this one tip could save you a ton of headaches and points on your next test.
Here's the deal, the trap. Your calculator is smart, but it has a blind spot. When you ask it for an inverse tangent, it can only give you answers in quadrants 1 and 4. It literally can't see the other side of the graph. So, if your vector is actually pointing into quadrant 2 or 3, the calculator's answer will be wrong. The fix is simple though. You just have to add 180 degrees to whatever it spits out. The golden rule is always check which quadrant your vector is in first.
So we've been deep in the numbers with components and angles and all that. Let's zoom back out. Why did we do all this? Why do vectors actually matter? Because once you know what to look for, you start seeing vectors everywhere. Remember our ship at the beginning? That's navigation. Pilots and captains use this stuff every single day. In physics, literally every force, from gravity pulling you down to the wind pushing you sideways, is a vector. Engineers use them to make sure bridges don't fall down. And the amazing 3D models in movies and video games, all built with vectors.
So now you've got the toolkit. You can start to see the world in this new way. The next time you feel a strong gust of wind, or you push a heavy door open, just think about it for a second. What are the forces at play? How would you describe them? Not just with how much, but also with which way.